if I ignore the lambda, then this is going to be d to the dk with some 2 pi's. Again, I'm going to ignore all the 2 pi's. Okay, and then it will look like e to the I a dot x over k squared plus n squared. Agree with that? Right? Okay. So this c to the d, so there's one c to the d sitting there. Now, I'm going to come over here and do this x integral, because once I write it in terms of this integral over k, all the x dependence sitting in the plane wave, right? So let me do it out. So it says psi z squared of 0 is equal to, up to some constant, okay? So I'm writing this squiggly equal to. So there's a c to the d, and then I'm going to exchange the order of k and x integrations, right? So what does it look like? It looks like d to the dk, and then there's a k squared, so that's m squared, and then there will be this integral here. Okay? You can see it's going to give you a Gaussian in k. Right? Can everyone see that? When I do that integral, it's just going to give me a Gaussian. But of course, the dimension of the integral has to come out. So it has to be c to the d again. Right? Okay, so there's another c to the d. Right? Sorry? No. The x integral, right? It's going to look something like e to the minus c squared k squared, maybe over 2 or something. Okay, I don't even care about 2's. Okay? It's going to be something like that. And then there's the k squared plus n squared. Right? Okay? Good. Now, remember that this c is really the same as 1 over n. Okay? So, let me take this c and scale the k affine to the c. Okay? So let me define a new variable which I will call y, a vector which is c times the k vector. Okay? Now this m squared is 1 over k squared. Okay? Now, what is the net result of this integration? So there is a c to the 2d, right? That came from here and here, right? Now I have d to the dk, which is the same as d to the dy, c to the minus d. You agree with that? Okay? And then there's an extra c squared here, sorry, that's d plus 2, right? And then it looks like 1 plus y squared e to the minus y squared over 2. Okay? Good enough? So the net result of all of this, now look at the y integral. It doesn't depend on anything. It's just some pure number. I don't even care what the number is because I've dropped all kinds of numbers. Right? Okay. So this thing then looks like c to the d plus 2. Alright, that's the left hand side. Okay? Good. So now let's compare. Let's apply this criterion and see what happens. So, I have on the left hand side c to the d plus 2. This should be much less than the square of this. Right? So that should be c to the 2d, dc minus t, let me call it this, t minus dc to the 2 beta. Okay? Good. So what this says is that 1 should be much less than c to the power d minus 2 dc minus t to the 2 beta. But what is c? So c diverges like t minus tc to the minus mu, right? So this entire thing here looks like t minus tc. So there's a 2 beta on top, right? Minus mu times t minus 2. You agree with that? So what this is telling you is that this power had better be less than 1. Otherwise there's a problem. Right? So now let's look at the mean field exponents that we have. Right? The mean field exponents are what? Beta is a half and mu is also a half. Right? So the condition we want, if the criterion is to be true, right? If the criterion is correct, the condition we want is 1 minus 1/2 b minus 2 should be less than 0. Okay? Because this should diverge, so there is much bigger than 1. Alright? So this tells me that 1/2 of b minus 4 should be bigger than 0. Do you see that? Of course, I don't need the 1/2, but it's bigger than 0. So this tells you that this criterion only satisfies for d bigger than 4. Okay? So whenever d is less than 4, such as the world we live in, d equals 3, this criterion is not satisfied, sufficiently close to the critical point. Okay, and that is the reason why mean field theory fails in 3 dimensions.
Can D be some other dimension as compared to the spatial dimension?
Yes, it can. So there are certain theories where, for example, the time may scale differently than space. So here I'm just talking about space. But if, for example, you talk about quantum phase transitions, right?
No, even if you take only the spatial part, if
Yeah.
you have a order parameter, which is not scalar but tensorial, so does the dimension change or it remains the same?
No, it won't change unless you have something very special. So that dimension actually is really coming only from the fact, you will see very shortly where that dimension comes from, but really it comes from the gradient square. So if you're any kind of field, if it has a gradient square term, then this is inevitable, okay? But sometimes you have fields with very soft fluctuations. So for example, you may have a gradient to the 4th power, and so on. Then this criterion will be different. In fact, it will be even much worse. Okay, the critical dimension here is 4. That will be like 2 or something, okay? So it will be very bad in that case.
Does mean this fast criterion, phi square j equal to less than expectation value of.
Sorry, what?
The second equation now.
This one, yeah. This is the Ginzburg criterion.
What is physically mean?
Physically, let me say it again. So what you do is you take a correlation volume, because that's the volume within which the spins are correlated. Right? Because the correlation length tells you at what distance spins are correlated. So inside that correlation volume, the point is that you look at the average of it, that tells you how close you are to the critical point, right? If the fluctuation is much bigger than the average, then the whole idea of a critical point becomes meaningless, right? Because some parts of the system are critical, some other parts are not critical, some things are below the critical point, some of them are above the critical point, and so on. So it doesn't make any sense. So in order for a uniform critical point of the whole system to make sense, you need this to be true. Okay. Right?
But to interpret it like that, you should have something like a variance and a mean. Their ratio should be very less than 1. But is that coming about from here?
That is exactly what it is,
So
right? This is
your
the variance.
This is variance less than 0 kind of a thing. Because variance is x square average minus average x square kind of a thing, right?
Yeah, but the point is that if this condition is not satisfied, right, then the variance is going to be much bigger than the average. It's the same condition really, because the RMS is this minus that, right? In fact, I did a dirty little thing. without telling you.
Sorry, actually this is looking like negative. I might be misread.
Yeah, I did a very dirty thing without telling you. So really, what I computed over here was the connected part of the correlation. Okay, so what I actually did was this is the correlator of this minus the average square. Okay, it's the connected correlation. That's what I computed. So really, it is exactly what you are saying, that it's the RMS. This thing, let me call it the connected part. Okay? Connected part just means that you subtract the average square. Okay? Sorry, I just did it out
Otherwise,
right.
if you're saying your variance is negative, that doesn't make
No,
sense.
cannot be, of course.
Yeah.
Yeah. That's right.
And now it becomes that. Let's say.
Yeah. This really it really is the fluctuations that I'm talking about. Okay? Alright? So sometimes I'll do things like this without even knowing that I'm doing it, and you have to stop me here. Okay? Yeah.
What is the meaning of this zero in the bracket for these points? This zero.
Sorry, what? The zero? Oh, because I could take it at any point. Of course, it doesn't matter which point I take it from, right? All right? Good? This thing here, so it's the connected part.
We got this formula yesterday.
We actually should subtract.
But we didn't do that yesterday.
Not explicitly, but within.
Yeah, but we should get the same, I mean, it's just constant.
So this is the average minus the product of the two averages.
No, that's just a constant.
Yeah, but below the critical point, of course, the constant will have some value, right? So yeah, but this is what is represented by that. It's actually the connected correlation.
Below the, we are doing it,
Below the critical point.
we are doing this one just around the critical point.
Look, in order to have an average at all, right, you better be below the critical point. Otherwise, you won't even have an average on a parameter, right? Yeah.